3, 2, 1, let's go. Okay, so we are back here in this business because we're not finished yet with the shear force and bending moment diagram. So this, okay, shear force diagram of this is going to be very, very simple because you now have the 5.425, nothing else to interfere. So it's a straight line until it meets with the point node here. So it comes down to minus 2.575. So you see, first thing that you should notice now is that, of course, this is the magnitude of the point node. Okay. Second is that if you still think that this is a simple beam, you will not be able to close down your bending moment diagram because your bending moment diagram now must also reflect the fact that this is the member with n moments. Okay. So now you're going to use your sign convention. So let's take a look at the left end of member BC. Now you have this moment. And let me say that the sign convention that we use, universally is that this moment is positive, makes your beam smile. And this is the negative, okay? Please notice that there is a sign for the member or for the moment on both ends. So if you look at the left end and it's this direction, so that is this one. So it's a negative moment. So we begin with minus 44.4. And then because we have the positive shear area here, this moment is going to go up. So the question is, how much? And this positive area is, of course, equal to 5.425 multiplied by 4. So it's roughly 20 something. So that means this member will never see the positive moment, okay? Because this is only 20 something. So when you add them up with the already negative moment on the left end, it goes up to somewhere, but it never reaches the positive value. And let's play some calculation music. That is minus 22.7. And of course, this shear area, this one is a negative area. So it should bring this bending moment diagram down again to the proper value that you have on the right, which is minus 33. Okay. Keep in mind that this is the member in the frame system. So you are very highly likely to ever have the moment with, the member with the ends with 0 moment. Okay. You must be true to the free body diagram that you have. This is the free body diagram that we have. You know that you have this moment. So this value must be reflected on our bending moment diagram. You have this value on the left. This has to be reflected on your bending moment diagram. Okay? And I forgot to mention one thing, that is when you look at this is clockwise moment on the right, which is again negative moment. Okay, so it turns out to be negative value here. You see how everything is related. It has to be related always. You have this free body diagram, so you must have this bending moment diagram. And the shear force diagram must also lead to the proper value in the end. Always. Okay? So that's the end of member BC. We can move on to the last one. Okay? Now it's gonna be fun because you can look at it from left or from the right to try to do your diagram. But for me, this is my preference. You don't need to do that. I always look at the frame like I sit inside the frame. So I when I draw the diagrams, I will look, say, from, you know, look at this direction, this, and then that. It conveniences me a little bit. Okay. So for this, my eyes will be here. The eyelashes and stuff. You know, I look at this direction. So I see, and I begin from this. Okay. So I see the positive shear now, right? Because it is. I look at this direction. So this becomes my sign convention. Go up and then down. So it's a positive shear. Okay. So my shear force diagram, I begin from this point, point C. So it's a shear of 8 going to the right or going up in this direction. So it goes up 8. And nothing to interfere, so it's constant. And then until it meets this 5 tons, it's down to 3 here. And then 0. Okay, so that's my shear force diagram. And I have the positive shear. And when I look at this from this direction, now I can see that the bending moment diagram is this. So it is, of course, a negative moment. And that is my minus 33. Okay, this is, no, not this. Let's bring it down here. Shear force, no parentheses. Shear force diagram, unit in tons. This is my bending moment diagram in ton meter. So okay, I have minus 33, and then I have this positive shear area. The total area here is 8 multiplied by 3, right? So that's 24 plus. So that should bring this bending moment up to minus 9. And here the area is 3 plus 3, so it's 9. So at last, this bending moment diagram comes down to 0 at this point. So that means if you pay close attention, this portion doesn't have moment. It can't, because the shear has to be 0 by then, right? So that concludes our shear force and bending moment diagram of member CD as well. So is there any question? I take that as a no. Okay, so let's move on to the next example, and I'm gonna spice things up a little more. Now you're gonna have this, the load that is not perpendicular to the member. So we need to do some exercise to change the nature of the load into the ones that the one that is perpendicular to the member and another that is parallel to the member. Now, before we dive into this right away, let me remind you that, you know, when you draw the bending moment diagram, you need to have the force that is perpendicular to your member, or to say it very precisely, to the principal axis of the member. If you have a case like this, you know that this force does not produce just the bending moment. It also produces the axial force. So it is your job to, you know, take the component that is perpendicular to the member and then parallel to the member. Now, only this red component, or the component that is perpendicular to the member, that will produce bending moment. The blue component or the component that is parallel to the member will not produce the bending moment. You guys understand this, correct? So if you have the load that is not, say, perfectly perpendicular to your member or the principal axis of your member, it is your job to realize that only the component that perpendicular to your member will produce bending moment. So if you have a case like this and then you proceed to use just this one, to calculate bending moment, you are wrong because you are including the horizontal or parallel component in the calculation of bending moment as well. So that's a simple idea, really. Now, in this part, when you look at this is the load that is normal. You can have your inclined load. I mean, you can have your inclined member, and then you have the load that is not perfectly in line or parallel or perpendicular with your member in that matter. Okay. This is only natural because, like, for example, the gravity load in the inclined roof, the gravity is always downward, but your roof may have some slopes. Yeah, that is also possible. So we have to find a way to recognize only the component that is perpendicular and parallel to your member. Okay, is there any question on this one? Who's Noah? He's a cake, right? So,
excuse me.
Yeah, sure.
Some questions that have just come to my mind. Is there any phenomena that there is a moment, but there is no shear?
Oh, excellent question. There is. Yes, there is. It's called pure moment. So, you know what? I think you deserve some answers. So let me try and do this. We can have a beam like this, can we not? Moment. Probably. So let's say, I'm going to show you the real case now. Let's say I have a beam. And then I put two equal loads like this. You know, let's say generally they would do at the 1/3 location. So it doesn't matter. Let's say this distance is equal, A and A. So that would mean your reaction is P and P, right? Correct? What would be your shear force diagram? What would be your shear force diagram? P and P, and then P and P. Is this our shear force diagram, folks?
Yeah.
Yeah. What's that? Zero shear. What's your bending moment diagram? You have the positive shear area. And it's a constant shear, so your moment is linear. How much is that? TA, right? So what's going to happen here? Moment zero? No.
And constant.
It's constant. And then this is minus PA, so it comes down to zero. So is that the condition where shear is zero and we have moment?
Yes, probably.
Probably again. How can you say probably? We have the correct shear force and bending moment diagrams, right? This truly is constant moment. Ideally. And this is a setup of the beam in the lab where they want to truly explore the effect of bending moment on the beam right here. We assume that the shear is zero. So you have pure moment on one free body diagram of the beam, which is this free body diagram, right? I can erase the support. And that becomes the free body diagram of this piece. Yeah. And
okay, I just look back and wonder if our material testing lab, it means that the self weight is eliminated.
I was going to say that, but you are quite quick. Self weight has to be neglected, not eliminated. Let's say it's minimal compared to this moment. Of course, it's there, and you will never have truly zero shear. But it's small enough. Let's say, you know, if you include the self weight into this, what would your shear force diagram look like? It's gonna look like this, right? With the slightly change in the shear. So if that slope is small enough, we say we neglect it and say this is as close to the pure moment as we get. Okay, we can neglect so many things. Just like the truss, right? I talk about the truss, right? Two force member. So where's the weight of the truss? We neglect it. It's there, but we neglect it. So truss, there's always moment in your truss member due to the self weight, but it's small enough that we can say, I didn't see it, like that.
Thank you for your answer.
Sure. And I'm saying this because this is real. This is what we do. Okay, we try to investigate the effect of moment on our materials. So this is the setup that we use to try to get the pure moment. Just like, you know, one more thing, because you asked for this, so let me go off topic a little bit. If I have one, say, piece of whatever that is, and I want to apply the shear, I want to fail this member by shear. No. So that the shear stress in this area is simply, what's the shear stress? This, right? Is V over A. Is there such thing as pure shear? How can you fail one material completely by shear? The answer is no. Unless you cut it with like a very sharp Japanese samurai sword. And you have to apply the force so fast that it just cuts through in millisecond, like that. Because otherwise there will always be deformation by small bending moment in the area. The same thing. So that's why we are engineers, you know, we are not scientists, that everything has to be exact. We know when we can neglect something so that our solution is more pragmatic and say it's more achievable. If you continue to look for the accurate answer on everything like scientists, you know, you can't do anything. You just can't. Just like, have you ever thought about how many degrees you have to turn your steering wheel in order to turn your car into ChemUTT onto ChemUTT campus? Have you ever measured the rotation of your steering wheel? Or have you ever measured the force that you apply on your acceleration pedal on your car so that, you know, it reaches the one specific speed? Sometimes we can neglect some things, right? That's the beauty of life. Okay, so very good question. So let's go back to this. Okay, so now we need to do this. Now let's say we'll begin in the calculation of the reaction as usual. Before that, you need to know that you have one upward reaction here, and then one there, and then one more there. Okay. Now I'm now caught between two minds. Should I still show you how to calculate reactions or should I not? But instead of show you, I'll show you different things, and then I will not show you how to calculate reactions anymore. Say this has to be 6, right? Because 6 is there. It's the only horizontal force that we have on the system, so that has to be 6. But then this 6 will create moment, and then you have that. So the results of this will be based on this load and then the moment these two loads create. But before I went on, I remember in the last Friday session that I talked about one group about this. So when you look at this, if I replace this frame, I wish to use crazy like this. Okay. I want to use black. Why it's not black? Not black enough? Okay. Now let's say if I don't have a frame at all, I have one piece of whatever that is. Maybe a rigid body or anything. See, now we don't have any frame. We just have this. One rigid body instead of a frame. But I have this same forces acting on the system. Okay? We have this uniform load acting here on this rigid body. Then we have this load acting here. And I'm asking you to calculate these three reactions. Would I get the same answers or would I get different answers? Would I get the same answers or would I get different answers? As long as you live in the elastic world, now it doesn't matter what the shapes you have. Probably again, you have to be confident. You're good enough, okay? So if somebody asks you if you win the lottery, you know, and you have the number one lottery in your hand, you say probably no. Okay. Thing is, as long as this is elastic, it doesn't matter what shape we have. I'm going to remove this. Okay. I can change the shape of the frame into something like this. As long as the reactions are in the same location, like this, and the load is the same, like just like this one, I will always get the same reactions, regardless of the shapes I'm dealing with. So when you can see through this phenomenon of the reaction, the configurations of the frame should not matter. Okay, so as long as it is the elastic behavior. So you don't get confused by the shape of the frame. You just go on and calculate the reaction just like you do with statics. It's just just one set of three unknowns. Okay, it doesn't matter what shape you have. So I don't think I need to show the calculation of the reaction anymore. Okay. So let's say this is 8.1 tons. And this is 9.9 tons. Okay. And you can always take moment. And this is, remember that this is the vertical uniform load. And the total load here should be multiplied by the true length. So the total load, let's say P here should be equal to 3 multiplied by 6 or 18. So you see that my reactions and, you know, the sigma Fy is 18, but it's not 9 and 9 because of the effect of the moment. Okay? Is there any question? Crystal clear, I suppose. So let's try to do, okay, should give some name first, right? A, B, C, D, and E. Okay, so let's go with member. Wow, I have 4 pages and I have 3 left, and then 1, 2, 4 members. Okay, that's fine. So let's do AB. This is AB. Ta-da! You know, we have the reaction of 8.1. So I don't think I should have to write anymore, right? That this is going to be 8.1. So that, in a nutshell, for member AB, over and done with. Okay, we don't have anything more on member AB. And you can just go ahead and say no shear force diagram, no bending moment diagram. Okay, and if you guys wish, we can also start working on the right side at the same time, right? I wish to say simultaneously, but you know, some of you may not know what that means. But you guys should know the meaning of the word simultaneously, okay? Which means at the same time. So I'm just going to work on member DE right away. DE. There's another lean column. I don't think so, because we have a hinge here. And we have the reactions equal to 9.9 and 6 there. And actually, don't forget that you also have the external point load applied at point D, which if you wish to write the free body diagram of point D or joint D, you should see things more clearly. Okay, but now this is the free body diagram of member D, so maybe it's better to remove this for the time being. Okay, so let's say if you look at member D now, you can see that oh, if I don't include that, I cannot have the equilibrium, so I must include that. Sorry. 6. Okay, so now we know that this has to be 9.9. But because, you know, we have 2 6s that do not coincide, so we know this couple is going to give you the clockwise moment. So we have to have the counterclockwise moment at this location. Okay, and that moment at D is basically equal to 6 multiplied by the length of the member, which is 7.5, which is in the end, that's 45, isn't it? Yeah, 45 ton-meter. So clearly we now have the proper free body diagram for the 2 vertical members, which you normally call the columns. So now we have a choice to go through 2 more members, the one with the problematic load and another one, it's a bit more simple. And since we're gonna have to take another break in 15 minutes because we began late, let me try the more difficult one first, okay? So let's go to member BC. Now you actually have the load in this direction. Now this load is, of course, not perpendicular to the member nor parallel to the member. So we need to find the 2 components, one parallel, one perpendicular to the member, so that we can work on our member properly. Okay, so now when I want you to draw the free body diagram properly, I don't need this. I want you to be able to turn this into the uniform load that is parallel and perpendicular to the member. Okay. Now, keep in mind that one thing that you can do is that no matter what you have here as a situation of the load that is not perpendicular to the member, you can always complete the internal forces at the end of the member. So that is 8.1, right? So you see, this total load, I think we did that, it's 18, right? Total load here is 18. So let's say by sigma fx equal to 0, you can calculate for your VC. It's gonna be 3 multiplied by 6 minus 8.1. So now you know that's at 9.9. It's gonna end smoothly because it's equal to the reaction on the opposite end, on the opposite side of this string. Now you can also proceed to calculate the moment at C as well without doing nothing with the load. So we can take moment at C. So now you have 8.1. Now, because we need the distance perpendicular to the force from the point that we take moment, so this can still be used. That is 6. 8, so we have 8.1 multiplied by 6. Now remember, it's a uniform load throughout the span length. I can just easily write this as minus 3 multiplied by 6 squared over 2. That's WL squared over 2, folks. Okay? So that should turn out to be 5.4, right? So maybe I should do it properly. That's a moment. Okay, so MC plus that minus that. Okay, so we have MC equal to 5.4 ton meter. So you see, you can actually calculate the forces at the ends of the member without having to do anything with the load. But once you want to draw the shear force and bending moment diagram, you cannot use this anymore. You must turn this into the perpendicular component. Okay, so what do we do? How do we do it? So here comes the fun part. You need to use a little thing from high school called trigonometry. Okay, so let me use different color. Let's say if this is my angle. Okay, I need the force perpendicular to this. Then another one will be the one that will be parallel. Try to use some fanciful colors to help you guys out. Okay, so if this is theta here, what is theta on that? This one or that one? That's your trigonometry, right? So if you can't see, there are two ways to look at things, okay? First is you can see this is, there's another triangle in here. That's a triangle. And then this is another triangle. Okay. This is 90 degrees. that is 90 degrees. This is the opposite angle, so they must be equal. So if this is theta, that is theta. See that? Beautiful trigonometry. Or you can just see that, you know, it's hard for me to do it for you here because I'm not in the classroom, but if you can see that the member rotates with this angle, just how much, if the load is perpendicular, how much the load rotates. So the angle must be the same, you know? So anyway, so that's the angle, that's the angle. So now you know you have to take the cosine to get the force perpendicular to the member. But it doesn't have to be cosine all the time, okay? Please keep your form free. So that's the cosine. We can go back to this, but unfortunately for your starting point, I give you 45 degrees. So that is 6. That is 6, meaning this is 45 degrees. So sine is going to be equal to cosine in this case, but you don't think you're going to be that fortunate in the real life, right? No, 45 degrees is something that if you get it in real life, you should probably buy a lottery, okay? So we have here, that's our angle. So now we need only the orange component that is perpendicular to the member. So how do we do it? First, we must make sure that the entire load is accounted for. And the entire load here is, of course, 18. That is your total load, okay? So the load that is perpendicular to the member becomes 18 cosine theta. Correct? That is your total load perpendicular to the member now. The total load 18 comes from, let me try to write more information for you, okay? The total load, no, that's not, okay? Let's say this is omega. So the total load, let's call it, how do I call it? Q? QB, okay. Is 3, that's my omega, right? Then multiplied by 6, which is the length in the direction of the load. So now the load that is perpendicular to your member is 18 cosine theta. That is the total load, okay? Total load perpendicular to member is 18 cosine theta. That's a total load. But another thing that you cannot do is to change the nature of the load. If it is a uniform load, it must remain a uniform load in the end. So we now know the total load that acts on the member. We need the uniform load. We don't need the total load. So to reverse this back to the uniform load, we therefore, let's call it omega prime. It's gonna be 18 cosine theta divided by, let's say, L prime, the length of the member, the true length of the member. Okay? So, with that said, because the degree is simple, so you can easily calculate this as a 6 square root 2, right? So that means this is equal to 18. The cosine is 1 over square root 2 divided by the length, which is 6 square root 2. So you can see there are two components of trigonometry in your equation. Okay, so in the end, this W prime is equal to 1.5 what number? Yes, ton per meter. Okay, this will be the uniform load that is now perpendicular to your member. And you must use this to calculate your shear force and bending moment diagram. Now, if you are curious about another component, yes, there will be another component that is the uniform load that is now parallel to your member as well. So you can calculate it with the same approach because this guy is 18 sine theta. And so the uniform parallel load will become 18 sine theta divided by L prime. So you can calculate the internal forces at joint C by simply using the equilibrium in typical XY direction. But in order to calculate the shear force and bending moment diagram properly on member BC, you need this. Okay. Now let me do one more thing to you. Hope it helps. Let me recap this again. In the beginning, we can always calculate this, you know. You will have the equilibrium under this condition, right? It's the same load. And I can say that we are looking at our system from the typical XY axis. But now, if this is under equilibrium, it means that I should actually be able to look at my same structure, but this time I twist my reference axis into this X prime and Y prime as well. So now I have this. And I have this. It's the same force. But I twist the reference. If the first one can be under equilibrium, so is the second one. Am I right? Have you done something like this in statics before? Okay. So that's it for the second session. You guys can take a 15-minute break. But as usual, before the break, is there any question? And I think because we missed so many interesting questions in the last session, so I'm just going to keep the record on in case there are some interesting questions, okay? Questions, folks? Question 1, 2, and 3. No questions, so I'm just going to stop the record first.